Lesson 2, Rational Exponents. So we're going to go through some of the exponent laws that you know from grade 9, as well as some of the exponent laws that you learned in grade 11. So starting with the product rule, when multiplying powers with the same base, you add the exponents. So you add the exponent of b plus c when the bases are the same. When dividing powers with the same base, you subtract the exponent. So this is the quotient rule that you learned in grade 9. So if you have a to the exponent b divided by a to the exponent c, you get a to the exponent b minus c. The power of a power rule, when a power is raised to another exponent, you multiply the exponents. So you have a to the exponent b multiplied with c. When a base is raised to a zero exponent, so this is a zero exponent rule, the result is always 1. So x exponent 0 is equal to 1. And then the negative exponent rule, when a base is raised to a negative exponent, you write the reciprocal of the base to a positive exponent. So essentially, if the negative exponent is in the numerator, then that part moves to the denominator. If the negative exponent is in the denominator, then that part moves to the numerator. Okay? So a to exponent negative m, because you have a negative exponent here, you have an imaginary 1 in the denominator. So if you write the reciprocal of the base in this case, you get 1 over a to a positive exponent of m. Similarly, if you have the negative exponent in the denominator, then you move this up to the numerator to get a to the exponent positive m. If you have a fraction to a negative exponent, you write the reciprocal of the base, so that would be b over a, and you would change the sign of the exponent so that it is positive as well. Okay, what we're going to be looking at are rational exponents. So before we do that, we need to look at some terminology. So here's a couple of terms that may or may not be new to you. Starting with rational numbers. Rational numbers are numbers that can be expressed as a ratio of two integers. Or in other words, you're just looking at a fraction. Okay? These fractions have to have positive or negative whole numbers. That's why it says integers. So that you can't have any decimals within your fraction. So here's a few examples of rational numbers. 0.5 seems like it's just a decimal. However, you can rewrite this as a rational number by writing it as 1/2. So you could write it as a ratio of two integers by writing it as 1/2. So any number that you can write as a ratio of two integers is considered a rational number. Rational exponents, which is what we're going to be looking at, are exponents which are fractions. So essentially you're looking at a term that has an exponent in it that is a fraction. And what we're going to be doing to these rational exponents is finding a different way of writing them so that we can actually evaluate them. Okay, and we'll see that on the next slides. So exponents in the form 1 over n. So if you have a rational exponent that's in the form 1 over n, much like the example that we have here. So if you have a to exponent 1 over n, you can rewrite this from exponent form, so the first form is exponent form, over to radical form, or power form to radical form. I'm going to rewrite that for you. So this is in power form, and what we want to write it in is in radical form. Once you write it in radical form, then it's a little bit clearer to evaluate. Okay, so if you have an example like 9 to the exponent 1/2, notice that the exponent on the 9 is a fraction, as opposed to what you're used to seeing, which is something like 9 to the exponent 2. This is something you know how to evaluate. You know that this is going to represent a growth, and this growth would be a value of 81. You know that the value is actually growing when you have an exponent that's a whole number like this. Okay, so we're not going to be looking at those kinds of examples necessarily. We're going to be looking at examples where the exponent is a fraction. So in this case, if I use a little rule that's here, notice that the value in the denominator of the exponent becomes the value inside the dip of the radical. Okay, so this is actually the inside the dip of the radical. So if I wanted to rewrite 9 to the exponent 1/2 in radical form, the easiest way to do it is to draw the radical sign first. And you'll notice that the base goes inside the radical, so this becomes a radicand. And that the exponent here, the numerator is not really making a difference, but the denominator here goes inside the dip. So I'm going to write the denominator of 2 inside the dip that's here. So essentially what I'm looking at is the square root of 9. Or in other words, I'm looking for some number where if I multiply it by itself will give me an answer of 9. So we all know what that is. The answer in this case is 3. And if you're unsure, you can always evaluate 9 to the exponent 1/2 on your calculator. But what you will be asked on your assessments is to rewrite the the power form into radical form and then evaluate it from there. Okay, so just some things you need to know about the variables here. First of all, the denominator of the exponent, which is n, has to be a natural number. Natural numbers are positive integers only. So integers can be positive or negative, but natural numbers can only look at positive integers. N is also called the index, so once in a while you may hear me call the value of n the index. So in this case, 2 is the index, 9 is a radicand. Okay, couple things to note. If n is an even number, so if it's a number like 2, 4, 6, 8, etc., then a must be a positive value. So that means that the base must be a positive value. So let's look at a couple of examples to see why this must be true. So let's say we look at 9 to the exponent 1/2 versus 9 to the exponent, negative 9 to the exponent 1/2. Okay, so here we said we're looking at even numbers for n, so the denominator of the exponent has to be an even number. But then it says a must be a positive value. So let's think about why a has to be greater than or equal to 0. So if I rewrite this in radical form, this becomes 9 in my radicand, 2 is the index, which is something I've already evaluated, and I know the answer here would be 3. Now if I do the same thing in this case, draw my radical sign first, negative 9 is my radicand, 2 is my index. Notice that now I'm looking for the square root of negative 9. And we know that you can't actually evaluate the square root of negative 9 because any value multiplied by itself an even number of times results in a positive answer. So it's very tempting to say that maybe the answer is 3 here, or maybe the answer is negative 3 here. But if I multiply 3 by itself, I get positive 9. If I multiply negative 3 by itself, I get positive 9 as well. So this tells me that this is not something I can actually evaluate. And so that's the reason why the value of a must be positive when the value of n is even. Okay? So this one's fine. This one is not fine. Okay? However, if the value of n is odd, then a can be any number. So let's look at an example where the value of the denominator in the exponents is an odd number. So 3, I won't do 1 because that's not very interesting, but 3, 5, 7, 9, etc., etc. So let's say you had 8 to the exponent 1/3 versus negative 8 to the exponent 1/3. Now 8 to the exponent 1/3 is equal to, if I write this in radical form, 8 goes in the radicand, and then the 3 goes in the index, so the denominator here goes in the index. And I know that the cube root of 8 means some number multiplied by itself 3 times will give you an answer of 8. So 2 times 2 times 2 gives you an answer of 8, so I know that this is going to be equal to 2. If I do the same thing here, draw my radical sign first, negative 8 is your radicand, and if I include the 3 in the dip here, now I'm looking for the cube root of negative 8. So some number multiplied by itself 3 times will give me a value of negative 8. And if I check this out, I know this would be negative 2 because negative 2 multiplied by itself 2 more times will give me an answer of negative 8. So in this case, when you have the denominator of the exponent as an odd number, then the value of the base can be any number. Okay? And the reason for that is because any value multiplied by itself an odd number of times may result in a negative answer or it may result in a positive answer, depending on what your base is. Okay? So if n is odd, a can be any number, or the base can be any number, but if it's even, then you have to have only positive bases. Okay, exponents in the form m/n. So this is the one that's a little bit more interesting. And this is true for all exponents that are rational numbers, including the one that we just looked at. So in general, if you have a to the exponent m/n, the n value here represents the index in the radical, so this goes inside the dip. But then what does the m represent? M actually represents the growth that you normally have. So there's 2 ways of rewriting a rational exponent. So there's 2 ways of writing a power that has a rational exponent. One way is to look at the growth part first and then the root, and then the other way is to look at the root part first and then the growth. Either way doesn't matter. Some ways are easier to evaluate than others, but regardless, you'll notice that the denominator is always in the root, and the numerator is always your exponent. Okay, so the numerator is always your exponent that shows an increase in the amount, whereas the denominator represents the root that you're looking at. Okay. M and N both have to be natural numbers, so they're both positive integers. And an easy way to remember this, and this is a way that I learned when I was in high school, is that when you do have a rational exponent, sometimes it's hard to remember where the m goes, whether it represents the exponent part or whether it represents the root part, and then where the n goes as well. So the way I remember it is, when you are looking at rational exponents, use something called flower power. And so what this tells me is the dividing line is sort of like, the dividing line here is similar to the ground that you're looking at here. And if you think about what's happening above the ground, there's the growth in the flower, so you actually see the flower here. So this represents the growth part here. And then if you look at the bottom part, you have the roots all along the bottom. And so that's how I remember that the bottom part here represents the root. Okay? And so that's how I would remember it. So I would think of it as, okay, the numerator is my growth. The denominator is my root. And so if I was to rewrite this in radical form, I would start first by drawing the radical sign. I would put in the base underneath the radical, so in the radicand. And then I know that the bottom part represents the root, so that goes in here. And the top part represents the growth, so that goes here. Okay? And again, it doesn't matter whether you look at the root first and then the exponent, or whether you look at the exponent first and then the root. Either way, the growth and then the root, or the root and then the growth. Either way, you can still get the same kind of result. Okay? Some ways are just easier than others.